In this lecture, we're going to discuss the optimal binary search tree problem. So in this problem, we're giving a list of keys that are sorted, and we want to put them into a binary search tree to be accessed later. We're also given a list of access frequencies. So these are, in particular, Fi is the number of times we expect AI to be accessed in the tree. So our goal is to compute a binary search tree that's consistent with those keys so that the total access cost is minimized. In other words, we want to, given information about the frequencies, minimize the total cost of accessing these keys. So let's just look at an example. So here we have an array A that's sorted, and these are the keys to the tree. And here's a corresponding valid binary search tree. So the key property of binary search trees is if you have a key in some node, then every key in the left subtree has to be smaller than it. So here 1 and 2 are smaller. Everything in the right subtree has to be larger than it. So these are all larger than 3. Similarly for 1, the things in the right are larger than it, things in the left are smaller. Okay, then F in orange are the accesses. So 3 is accessed 10 times, 2 is accessed only twice, and so on. And our goal is to build this tree structure, so what the tree looks like, to minimize the total access cost. So what is the total access cost? Well, it's just how frequently a node is visited times the depth of the node. Because the deeper a node is, the longer it takes and the more difficult it is to access it. So one thing to notice is that the highest frequency thing generally needs to be close to the top, because if you're accessing it constantly, you want to at least be able to slow down the cost per access, which would be the level. So for this specific example, the cost would be 1 times 10, since the root 3 will be accessed 10 times. Then we have 2 times 5 plus 6. That's for node 1 and 5. So they are frequented or accessed 5 times and 6 times respectively. And for each access, we have to first go through the root node and then go through to 1. So that's why the level is appearing in these costs. Okay? Another way to say this is it's the frequency of each item I times the number of ancestors. That's equivalent to the level. So we want to somehow characterize this cost recursively so we can do backtracking / divide and conquer type algorithms. So to do this, let's look at a specific element I, and let's assume it's less than the root. So in particular, if it's less than the root, then in the array A, it will be to the left of the root. So in this example, the root's 3. So key 1 and 2 are on the left side of the tree, and then the keys to the right are on the right side of the tree. So the sorted order also corresponds to the binary tree order, which is going to be important. Okay, so we have this particular element I less than R, and so because it's less than R, we know it's in the left tree. So what's the total cost that I specifically will incur? Well, that cost is exactly the number of ancestors of I times its frequency. And we can split this. So notice the number of ancestors are exactly the number of ancestors in the subtree L plus 1 for the root. So this is the subtree, well, this whole thing is the subtree L. And we notice this can be broken down to the number of ancestors of I in L plus 1 times f of I. So let's add a new page. So now we can kind of see how this might be recursive. So let's think of how many total accesses there are for the root. So the root R is accessed every single time, or let's say it's touched rather than accessed or requested. It's touched every single time anything is requested. So in total, the cost for just R is going to be the sum over all keys of their frequencies. So that's taking this +1 term and just distributing it out over every single key. So now we can update our cost for a tree and given set of frequencies by doing the following. Well, this is going to be the total cost for the root, which is Fi summed up, plus this is going to be the cost for the left side of the tree. And then F goes from 1 to R minus 1, because those are the only keys we consider on the left. And then similarly, we have the right side of the tree, and F R plus 1 to N. So this is a recursive formulation for the cost. And where is this coming from? Well, this is just coming from this fact here. So if we looked at the total cost that I contributes to the process, it's mostly the total cost it attributes to the left subtree. And so if we just considered the cost of the left subtree alone, we would get exactly the sum of the ancestors of VI in the left, in that term corresponding to I. So that gives us, this key claim gives us the recursive definition of cost. And now that we have a recursive definition of cost, we can try doing backtrack algorithms. So the first thing is the base case. If n equals 0, in other words, if there are no accesses to be done, then we'll have an empty tree which has 0 searches. So our algorithm, if n equals 0, just returns this. And it's optimal because of this. So I'm kind of combining the induction proof with the actual algorithm here. So now what's the key decision we have to make to use a backtracking algorithm? So what decision? So notice before, the key thing here is the root. Once the root is fixed, we are then recursively doing stuff, either computing costs or other things in the left and right trees. Also, the root's kind of the most important thing because its cost affects everything else's cost. So what decisions do we need to make? We're going to decide what the root will be for a given tree T. Or not for a given T, but for a given subset of A. Of the keys. So that's the decision we'll have to make. And then after we decide on R, we'll try all possible. Try all possible R. And have the recursion vary the cost of the corresponding best left and right side. So then if we do that, then we can just take the cost of R plus the costs computed to generate the total cost, and then we take the best total cost. So again here, we're focusing on optimizing the cost, not actually picking the solutions R, but once we've done this, we can easily modify the algorithm to output R, or all the nodes in the tree, rather than just the costs. So let's formalize this idea. So the problem we're going to solve is going to be the optimal cost, IK, and this is just going to be the total cost of the optimal tree for keys I through K. And in particular, we're only going to look at the f function, so really we'll just say f, I through K. So what's the recurrence for this problem? So the base case is easy. The optimal cost is 0 if I is greater than k, and so we have no keys. And so no accesses. On the other hand, if we do have some number of keys, well, we know the cost is the cost of the root. And the cost of the root is just going to be the total frequency for every single item in the subtree. And here the subtree only considers I through k, so that's why the indices are like that. And then we're going to try all possible roots from I to k, and pick whichever root gives us the minimal total cost. So in particular, the cost is the sum of the left and the right subtree. So this is going to be op cost I r minus 1 plus op cost r plus 1 to k. So one thing to notice here is because we need to maintain that this is a binary search tree, we're forced to have I go up to r minus 1, and we're also forced to have r plus 1 go up to k. Those define the left and right subtrees to ensure the tree we compute is a binary search tree. So that's why we're only considering those indices specifically, and why the root has to be in the middle of them. Okay? So now what's the solution to the entire problem? Well, we're just going to return op cost of 1n, because that's the whole array. So the running time we'll discuss next week, but what's the idea for correctness? Well, the correctness is directly proven by this cost analysis. So really, this was an induction proof itself. When we derived this, we got the proof of the algorithm. Because we know the cost is exactly this, and the recursion fairy is going to compute these correctly. And so if we have the correct cost of a total tree, and we're trying all possible trees, the whole thing is correct. So we pick the best root, and recursion fairy picks best left and right for that root. And so the fact that the cost can be decomposed into root cost plus left cost plus right cost implies the total cost is optimal. It's optimal because we optimized each individual component. And induction implied that we could do the left and right part successfully. So that gives the overall proof, the correctness. And that's it.